All right, so this video is going to be on alkene nomenclature, as well as a couple other things. But first, let's just draw out a few compounds that we should be able to name. Now, nomenclature, I usually kind of put a lot on you just because it's really just reading some rules. And so there's no reason for me to rewrite those rules. But I'll go over some examples of how I would walk through it. And so let's try this middle one first, just because it's just a straight up alkene. It doesn't have that OH in there. And so there's the alkene. What you want to do is basically number the longest parent chain that contains that alkene group. Okay, so that would be a 5. And so we would call that a pentene, changing the ending from ane to ene because it's an alkene. And then we number from 1 to 5 with the alkene carbon getting the lowest number. Then we have to label our ethyl and then our methyl as well. And then we put it all together in alphabetical order like normal. So it's pretty straightforward. One thing you just need to make sure you're doing is giving the alkene the lowest number and only numbering the first of the 2 carbons in that alkene. So notice we only said pent 1 ene instead of like a pent 1 2 ene. And so that's what I mean. Just the first number is all you write for the alkene because it's implied that the number 2 is bound to that, is part of that double bond as well. So we have a cyclopentene here. Now what we want to do is number it. So let's try one way. 1, 2, 3, 4. That gives the methyl the 4 position. But the other route, if we go clockwise, gives that first methyl the 3 position. And so that's actually what we want to go with because it gives the substituents the lowest numbers possible. And so the cyclopentene in this case, we're actually just going to leave it as that. And then we have a 3,4-dimethyl cyclopentene. We don't write the pent 1 ene on the cyclopentene because it's always implied that in a cyclopentene it's number 1. Now this guy right here is an OH, and we have an so it's an alcohol. We also have an alkene in there, right? And so this compound in general is just called an enol, as in alkene and alcohol. And we number from the OH, giving the OH the number, the smallest number. Okay, and so that pretty much means we have a 6-carbon chain containing the alcohol as well as the alkene. And so we have a 3 ene, we have a 1 ol, and we have an ethyl at our 4 position, right? So the way we write this one is a little weird, right? Because we have 2 different functional groups in there. We haven't seen that before. We write hex 3 ene 1 ol. Okay, so sorry, let me erase this E. There shouldn't be an E on the end of that ene. So 4 ethyl hex 3 ene 1 ol. That's a mouthful, I tell you what. But fortunately we won't really see too many of those nomenclature questions naming more than one functional group in it. So we're good on that. So go ahead and practice those ones. But we're moving on to stereoisomers of alkenes. So we know cis and trans already, right? But what do you call these two? Because are those cis or are those trans? That's kind of the question, right? We need to develop a new naming process to kind of allow us to distinguish between these 2 compounds because there's more than one. It's tri-substituted instead of di-substituted. So just for the sake of naming, we're naming that top cis compound. We're naming it but 2 ene. That trans compound is also a but 2 ene, and the way we distinguish between the 2 is just putting a cis in front of it or a trans in front of it because the groups are either on the same side or opposite of one another. Now we could do the same thing here as well, but if you look at just like the above compounds with the same name, we have pent 2 ene for both of these, and so we need to be able to distinguish between them. So at the 3 position, of course, we have the methyl group for both of them, and So again, the way we need to distinguish between these two compounds is using E and Z notation. Okay, so the way we do this is we have to kind of prioritize the groups that are on the left side of that alkene and the right side of that alkene. So what we're going to do is imagine we are slicing it in half and we're comparing that methyl to the hydrogen. And so we will prioritize them according to the Kahn-Ingold prelog system. So basically like as if we were assigning R and S, right? So the numbers are according to priority. So 1 and 2, 1 being the priority. That means, as you can see, 1 on this one is trans to the one, the ones are trans on the compound on the left. That means we would assign it as an E. Okay, and E is a German word. It's, excuse my German, Entgegen. I'm not sure exactly how to pronounce it, but it means opposite. So kind of like trans, right? And then Z is this compound on the right because the ones are on the same side of that pi bond, like the north side, if you will, the upper side. And that stands for zusammen, and that means together, also in German, right? And so, like I said before, this is kind of like a trans and kind of like a cis, right? Now, for me, I was always told, remember, Z is as if they're on the same side, kind of like Borat, right? Look at that face. That got silly. Same side. My wife. That's nice. Terrible Borat impersonation. I don't even know if he says all those things. I feel like I sound like Paul Rudd impersonating Borat. That's pretty much where I got my Borat impersonation anyway, so whatever. That's cool. Just remember that Z means that the priorities are on the same side, like as if they were cis to one another. Okay, so let's go ahead and try these problems. We will go ahead and note that the methyl and the bromine are the priorities. And so we already know that this is going to be an E compound, but let's go ahead and try and name it as well. So we have 3 carbons in there. That's a propene. We have a chloro and a bromo, which we're going to give the 1 assignment because they are going to be the priority. And then we've got a 1 bromo, 1 chloro, prop, 1 ene. And of course, that's an interesting one. It's long. And we don't want to forget our E in the front of it to indicate that that bromine is essentially trans to the methyl group, right? So again, the way we do this is just an E in the front with parentheses, and then anytime you're dividing a letter and a number, you have to put a dash. So that's why we have the dash right there as well. So numbering this compound on the bottom, we have 1, 2, 3, 4, 5, 6, 7. So remember that is heptene. Now, of course, we got to figure out where to number that. 1, 2, 3, 4. And then 1, 2, 3, 4. Okay, but if numbering from left to right gives us this first substituent at the 2 position. So we're going to give the alkene the 3 position as the start. So it's hept3ene now. And now we can just kind of tally up we got a 2 methyl, we've got a 4 ethyl, and also a 5 methyl. So go ahead and jam all of these together as one, going in alphabetical order, not including the di part of our alphabetizing, right? So because there is a 2,5 dimethyl portion of this, and so we still start with the ethyl, and then finish it with hept3ene. All right, so naming it was pretty chill, but we also have to identify whether or not it's E or Z, right? Because we have more than 2 substituents on that alkene, so we can't call it cis or trans. We got an isopropyl group, we have an ethyl, and we have like a sec-butyl there. Okay, so 1 positions are labeled, those are trans to one another, and so we assign an E to this alkene, and that's pretty much it. Cool, right? Get it right, get it tight. All right, so common names for things. You've seen these before, except for this one, methylene. A methylene group is pretty much like a terminal alkene. We've got pretty much a CH2 group. So oftentimes you'll hear a regular CH2, like in this cyclohexane ring, called methylene groups as well, because it's just a CH2. Okay, so this guy right here, we have this terminal double bond, but with an extra kind of single bond in between. This is called a vinyl group. Okay, now this compound in general is just called 1-vinyl cyclopentene, because remember, for the cyclohexenes or cyclopentenes, we don't really number it because the alkene is always given number 1. Now this guy is a little bit different than the vinyl group, and this is an allyl group. Okay, so remember we saw these differences in the substitution and elimination because that sp3 carbon in between is actually really important, and it allowed for like resonance. But this is an allyl cyclohexane group, and this allyl group, the way we can distinguish is because this carbon right here on the vinyl group is an sp2 carbon, whereas there's an extra sp3 carbon for the allyl group. Okay, so like vinyl halides didn't undergo substitution reactions, whereas allylic halides did, and their reactivity was similar to a secondary alkyl halide. Okay, in terms of like SN1 and E1. So let's do properties of alkenes. This again is pretty chill because we already know the general idea of alkene, or I'm sorry, of physical properties of organic compounds, and it pretty much just kind of holds true throughout the entire class. But there are subtle differences that we need to discuss for the new compounds that we introduce as we go. And so for alkenes, what we need to introduce is the idea of how cis and trans can affect it. So in general, alkenes are relatively non-polar, right? So they are just like alkanes in terms of that, because it's all carbons and hydrogens, right? So we have a low melting point as well as a low boiling point because they don't have very strong intermolecular forces. But and then also we have that they are insoluble in water for that very reason. They are non-polar generally. But so let's take a look at this cis and trans compound here. We have a boiling point of 4 for the cis and a boiling point of 1 for the trans. Why are they different? Think about that for a second, okay? So let's label these carbons in red. Those carbons right there are all delta negative, okay? That's because they are sp2. And these blue carbons here on these methyl groups are all delta positive. It's the slightest bit positive and the slightest bit negative. There's not much of a dipole there, but there is, because those blue carbons again are sp3, which means it's going to have more S character. It's going to be an electron donor, as we saw before with those R groups being electron donors. And then the red one is an sp2 carbon. Ooh, you almost made that mistake real quick. So, sorry, sp3 is less S character because it's 25% S, and then sp2 is more S character because it's 33% S character. But and then that there's the blue is still electron donor, and then the red is still an electron acceptor. Since it can accept electrons, it's delta negative. Since the blue can donate electrons, it's delta positive. And so we get a dipole kind of about this bond looking like this. These are opposing dipoles in the trans compound. And if we take a look at the dipole in the cis compound, they are going in the same general direction, right? So they are reinforcing one another. And that means that there is a net dipole, and that net dipole is just heading in the downward direction. So what does that mean? It means that it's slightly more polar than the trans, and that's why we get that 3-degree difference in the boiling point. Okay, so that's really the only thing different about alkenes in terms of what you might expect. You can have a slight dipole giving cis compounds a subtly different melting point or boiling point. Okay, so that's all, folks. Have fun with it.